Hi, my name is Adrian Rochek, and today I'm going to continue on with my next video for my project Collision Detection for the Blind. As a brief recap, the project I am working on aims to implement readily available technology onto traditional walking sticks to provide collision detection for the blind, improving the way of life for the vision impaired. To achieve this, microcontrollers, sensors, detection techniques, and other hardware are being bundled together to provide a safe, form factor, and unobtrusive device that can be easily attached and detached from currently available walking sticks. Initially, I planned on using the Texas Instrumental MSP430 as my microcontroller, but quickly realized that library support for the device was scarce compared to Arduino microcontrollers, making the project more challenging. To increase form factor and reduce weight, I opted to use an Arduino Nano, which has better library support for the LiDAR light sensor, making it easier to interface with and code. Additional hardware needed to be purchased to resolve unforeseen problems that arose during the initial implementation. For example, a 1.5 voltage drop was observed when powering 5 volts to the device over USB from the computer and also the power bank. This caused the servo to behave erratically and sometimes not function at all. To resolve this issue, a 4-cell AA battery holder with batteries was used, and a 9-volt battery was also tested. Usage of the 9-volt battery required the addition of a 5-volt regulator so the circuit isn't overloaded, but it did not provide enough current, and therefore the servo ended up behaving erratically anyway. The 4 AA cells gave a total of 6 volts, outputting 4.75 volts, and gave enough current to the circuit to power additional devices while providing full functionality at the same time. The initial for loop implemented in the code used to control the servo in the endless loop was changed to operate using an if-else statement. This was done because having method calls or extra code within the for loop would increase the delay of the servo and reduce sweep speed. Usage of the 9-volt battery required the addition of a 5-volt regulator so the circuit isn't overloaded, but it did not provide enough current, and therefore the servo ended up behaving erratically anyway. The 4 AA cells gave a total of 6 volts, outputting 4.75 volts, and gave enough current to the circuit to power additional devices while providing full functionality at the same time. The initial for loop implemented in the code used to control the servo in the endless loop was changed to operate using an if-else statement. This was done because having method calls or extra code within the for loop would increase the delay of the servo and reduce sweep speed. The video demonstrates the servo motor and LiDAR light sensor working in sync with the current circuit and voltage source implementation. When the LiDAR light sensor reads a distance of over 100 centimeters, the onboard LED will stay on, but once the distance is below 100 centimeters, the LED will turn off. This is to show that the LiDAR sensor is functioning properly. In this slide, I have attached some snapshots of my code and also output from a previous implementation while using serial interface and serial monitor. At the start of my code, the outside wire, LiDAR light, and servo libraries are included into the Arduino sketch. These libraries allow me to create a servo and LiDAR object to control the devices. Then variables store the servo pin number, measurement count, servo position, and Boolean rotate direction. The setup function initializes and configures the LiDAR light sensor, attaches the servo to the control pin, and initializes the onboard LED. The endless void loop recursively calls the move servo method, which controls and rotates the servo position using an if-else statement. As the servo operates, it makes calls to the measure distance function, which actively takes distance measurements by calling methods within the LiDAR library. In the coming weeks, I'll be adding an IMU with accelerometer and gyroscope to account for drift, acceleration and deceleration that comes from operating the device. Feedback sensors outlined in previous presentations will also be incorporated, and a case will be designed and 3D printed to house the devices together. An important goal is to reduce the overall weight of the project to decrease fatigue it may cause to the user by looking at alternative battery types.